I will now talk about two important topics in counting. One is the binomial coefficients and one is combinatorial proofs. Binomial coefficients is about coefficients that appear when we evaluate a term like x plus y to the n. And combinatorial proofs are proofs of equality where we use counting arguments to establish the result. Let's start with binomial coefficients. The binomial theorem tells us that if you have two variables x and y, then x plus y to the n is this term here, the sum from I equals 0 to n of n choose I, x to the n minus I, y to the I. Almost everyone knows this case for x plus y to the second, for example. If you look at x plus y to the second, we know that this is x squared plus 2xy plus y squared. If you look at this is the n here is 2, right? In this case, n is 2. So this is 2 choose 0, x. If I look at the formula there, x to the second, y to the 0, plus 2 choose 1, x to the first, y to the first, plus 2 to the 2, x to the 0, y to the second. And if you evaluate this, 2 choose 0 is 1, x squared, y to the 0 is 1, so this is 1, this is 1, and this is 2 here, this is 1, this is 1, we get x squared plus 2xy plus y squared. And you can use the same result for x plus y cubed and so on. So if you get a question of the form, for example, what is the coefficient of x to the second, y to the third in an expression where we are looking at x plus y to the 10, for example, you can use this formula to evaluate, or sorry, x plus y to the fifth. You can use this formula to evaluate that, okay? And it's very helpful for us to evaluate counting problems, because sometimes when we count, we get these kind of terms here. For example, what is the sum from I equals 0 to n of n choose I? So where would this, for example, arise? Suppose the question is, count the number of subsets of a set of size n. So if I ask you to count the number of subsets of a set of size n, you can say there are n choose 0 sets of size 0. There are n choose 1 sets of size 1, subsets of size 1. There is n choose 2 subsets of size 2, all the way to n choose n subsets of size n. This summation here is what that sum there I equals 0 to n of n choose I is. The question is that what is this summation? I can use the binomial theorem to evaluate it, because what's written here, the sum of n choose I from I equals 0 to n, this is basically, I can now introduce ones there, which are not shown here, but this I can look at it as I, n, sorry, not I, 1 to the n minus I, and I can add another 1 here to the I, right? Because I just multiplied by 1, I didn't do anything here, but I put 1 to the n minus I, 1 to the I, because now this looks like something I can apply the binomial theorem to. So this, I can take this to be the x, I can take this to be the y, and then what I have here is nothing but the binomial theorem applied to 1 plus 1 to the n, and this is 2 to the n. So this summation is 2 to the n. Indeed, if I ask you what's the number of subsets of a set of size n, it's 2 to the n. So one way to approach it is to say it's 2 to the n. One way to approach it is to say, well, it's the number of subsets of size 0 plus the number of subsets of size 1 and so on. Both are the same, okay? Let's look at another example here. What is this summation? Minus 1 to the I, n choose I. Again, the same thing I can do here. I equals 0 to the n choose I, and I can put 1 to the n minus I, and minus 1 to the I. If I look at it like this, now the binomial theorem allows me to say that if I take this to be x, and this one to be y. This is 1 plus minus 1 to the n, 0 to the n equals 0. This whole summation actually is going to evaluate to 0. And the binomial theorem allows me to do that. Okay. This n choose I is when I look at the x plus y to the n, and it is the sum from I equals 0 to the n choose I, x of n minus I, x to the n minus I, y to the I. This term here, this is what we call binomial coefficient, okay? This is a binomial coefficient. Okay. Let's see one more example. What is this sum here? The sum from 0 to n of 2 to the I n choose I. Same story. I can look at it and say, because I need to see x to the n minus I, y to the I. I'm seeing here something to the I, so what's missing is something else to the n minus I. So I can look at this as n choose I. I can look at the 1 to the n minus I, 2 to the I. Now I have, by the binomial theorem, I can take this to be the x, this to be the y. This is 1 plus 2 to the n. It is 3 to the n. So this summation here evaluates to 3 to the n. Okay, so it's a powerful theorem when we have summation of this form here, where we have these binomial coefficients, the n choose I, then we have one of the other terms, n choose I times something to the I or something to the n minus I. We can plug in 1 to the I or to the n minus I, and then use the binomial theorem to evaluate the sum. A second topic is about combinatorial proofs, and this is where we want to prove two quantities are equal. Okay, two quantities, usually two counting quantities, are equal. So I want to say that, for example, we just saw that the sum of n choose I from I equals 0 to the n equal 2 to the n, right? So for example, we saw this already, but suppose we didn't see it and someone give this to you and say, prove this is true. So prove this true, one way to prove this true is by using combinatorial proof. How do I use combinatorial proof? I approach the problem by looking at this here and come up with a counting problem or a counting argument. And then I can approach that counting argument in two different ways. One that results in the left-hand side, one that results in the right-hand side, in the left-hand side. So for example, for this specific one that I'm showing here, that the sum from I equals 0 to n of n choose I equals 2 to the n, I can say a counting argument is that I am interested in counting the number of subsets of a set of size n. If I say that, counting the number of subsets of a set of size n, here's one approach, one way to count such a set, such a number. So since I'm interested in the number of subsets of size n, I can say that I'm going to represent every subset as a binary vector of size n. Okay? And I will put 0 in an entry if I'm taking the element from set S. So suppose our set is A1, A2, A3, all the way to AN. And I am interested in looking at all the subsets of this set. So I can look at this binary vector. I say, if you want to take a subset that has A1, A2, A3, for example, only A1, A2, A3, you put 1, 1, 1 here, and the rest are zeros. If you want to take the empty set, the empty subset, you can put 0 in all places, right? So if I look at it like this, the number of subsets, it's the number of binary vectors of size n, because every binary vector corresponds to a subset. For example, the binary vector of size n where every entry is 1 is the entire set. The binary vector where every entry is 0, it's the empty set. The binary vector where only entry I is 1, the rest are 0, then AI is the subset contains only AI, nothing else. So if I look at it like this, then the number of subsets is 2 to the n, because we know the number of binary vectors is 2 to the n, using, for example, the product rule. But another way I can approach the problem, to approach the problem, I can say, well, the number of subsets, it's the number of subsets of size 0 plus number of subsets of size 1, and so on, right? I can add all the way of size n. Well, this here, the number of subsets of size 0, we know it's the number of combinations, it's n choose 0. Number of subsets of size 1, it's n choose 1, and so on. So doing this, I have actually showed the same counting problem, which is I want to count the number of subsets of a set of size n. If I look at it from the perspective of every subset corresponds to a binary vector, one instance of a binary vector of size n, then I get the right-hand side, 2 to the n. If I look at the problem in a different way, if I approach the counting problem as by saying, let me count the number of subsets of size 0, then let me count the number of subsets of size 1, and so on, and I add them, then I get the left-hand side. But both of them are these are two different ways for solving the same counting problem, so they have to be equal. And this is what we mean by combinatorial proof. So I wanted to show this summation on the left-hand side equals 2 to the n. I defined the counting problem. In this case, I said I want to count the number of subsets of a set of size n. Then I said, let me count it in one way by saying that the subset is basically corresponds. There is a one-to-one correspondence between subsets and binary vectors of size n. I got to the 2 to the n on the right-hand side. Then I said, let me count in a different way for the same counting problem by looking at subsets of different sizes and then counting their numbers and adding them. And then I got the left-hand side. Okay. So here's another famous equality known as Pascal's identity that says n choose k equals n minus 1 choose k minus 1 plus n minus 1 choose k. And the question is that how do we prove this combinatorially? Well, the counting problem that I can come up with here, I mean, if I look at the left-hand side, I can say counting, for example, the counting problem, okay? That we have n students. How many committees of size k can we form? Okay. So solution 1, or approach 1, let me actually call it not solution 1, but approach 1. It's the number of k combinations of the n students, right? Just take any subset of k students from those n students, then you will get a committee, and we know that this number is n choose k. So approach 1 gave me the left hand side, okay? Let me look at another approach to solving the same counting problem, okay? The second approach is, let's designate a certain student, okay? Let's consider a specific student, student X. Then we can say we have committees, we have the committees, or k committees of k students that include X. And then we have committees of k students that don't include X. What do I mean by this here? That when you are taking a committee of size k from a set of n students, then that committee, take any student in the group, okay? So let's call that student X. Then when you take a committee of size k, you have one of two options. Either student X is in that committee, or student X is not in that committee, right? So when we count the number of committees of size k, I'm saying let's count the number of committees that have student x in them, the number of committees of size k that have student x in them, and the number of committees that do not have student x in them. So committees that have k students, committees of k students that have x in them, well, if x is one of the students of the k students in the committee, then I now need to look at finding of the remaining n minus 1 student. I need to find k minus 1 students, right? Because of the n, I have already taken student x and I made it one of the k students in the committee. So what I'm left with is the number of ways I can choose k minus 1 students from the remaining n minus 1 students. If I don't take x, then what I have left is to choose k students for the committee from the remaining n minus 1, because x is not part of it, so I have n minus 1 students to choose from. X is not part of it, I still have k to choose from the remaining n minus 1. And this is why the number of committees of size k, it's the number of committees that have x in them, student x as part of them, plus the number of committees that don't have x in them. And that's n minus 1 choose k minus 1 plus n minus 1 choose k. Both arguments are solving the same counting problem, therefore both sides are equal. Okay. Let's look at another one here that's known as Vandermonde's identity, that says m plus n choose k equals the summation on the right. When you see something like this, m plus n, immediately you can think about it. Let's think about two types of objects, and we are counting over two types of objects. So for example, one way I would do this here, I would say that the problem is that we have m freshmen and n sophomores, and we want to select a committee of k students. Okay, I want to choose a committee of k students, but I'm not saying any other constraints. Okay, the k students can be all freshmen, they can be all sophomores, it can be a combination of the two. So approach one, again, as before, I can say, okay, I'm interested, count the number of k combinations from the m plus n students. So notice that in approach one, I'm not treating sophomore and freshman differently. I'm saying I have m plus n students. I want to choose a k combination of them. And this results in m plus n choose k. Okay? So this is approach one. Another approach is similar to what we saw before with Pascal's identity. Approach 2 is that saying that the committees, its number of committees, then you can look at it, its number of committees that have, for example, 0 freshmen. And if I take 0 freshmen, then I have to take k minus 0 sophomores, right? So this is one way to say, okay, it's the number of committees that have no freshmen in it, but it has k sophomores in it, plus number of committees that have 1 freshman and k minus 1 sophomores, plus number of committees that have 2 freshmen in it and k minus 2 sophomores, plus all the way to I have k freshmen and 0 sophomores, right? So I can look at this problem as, I can be more detailed about it. I say I'm going to look at committees of the committee will either have 0 freshmen and k sophomores, or 1 freshman, k minus 1 sophomores, or 2 freshmen and k minus 2 sophomores, and so on. Then if I look at them, if you look at these numbers here, what are they? So if I look at the number of committees that have 0 freshmen and k minus 0 sophomores, so we are looking now at, if I took the m to be the freshman here, so it's m choose 0 freshmen, and we want from the n to choose the k minus 0. For the second one, it is that we want to choose 1 freshman and k minus 1 sophomores, and so on. At the end, we want to choose k freshmen and n choose 0 sophomores. And it's the sum of these terms, which is the term that's written on the right-hand side there. Okay. So if you look at this problem, again, I want to count the number of committees of k students from a group of students that I designate m of them are freshmen, n of them are sophomores. One way to look at it is, let's group the students together, not worry about who's freshman, who's sophomore, and say, give me a committee of size k. So then that's just the number of k combinations. It is m plus n choose k. Another way to approach it is that, let's be detailed about it and distinguish between freshman and sophomore. Then I can say the committee can have 0 freshmen, k sophomores, and so on. And then I can get the right-hand side, okay? So combinatorial proofs operate like this. One has to be careful because it sounds like, there's hand waving here. There is no hand waving. If you are doing each one of these approaches, you have to be valid, writing a valid approach to solving the counting problem. And if you look at this, there are no holes in this argument here. In the approach 1, I was asked to form a committee of k students, and I have m plus n students. I know by the theorem that we learned that it is m plus n choose k. There is no hole in that argument. The second thing is, or the second approach, I am now distinguishing between the committees based on the number of freshmen and sophomore in them. There is no hole in it. I did not miss anything. I did not overcount anything either. So this is a very valid, very powerful proof technique. You have to be careful. You have to define the counting problem carefully. And then the two approaches you come at the problem from have to lead to the result that you are trying to prove here. Because there could be a third approach or a fourth approach that might not give me these terms that I have in the equality. This will not be helpful, okay? So you first look at the equality you're trying to prove, or the inequality, and the approaches that you come to the counting problem with have to be driven by the terms you are seeing in that. It's not an easy approach because you have to think carefully about what is the counting problem to begin with, and what are the approaches that I need to arrive at the left-hand side and the right-hand side.